Any questions about anything before we get started? So this is what's called the end game if you play chess. Right? There are 3 more lectures. Today we're going to do stimulated Raman scattering. Well, I'll tell you why as the lecture goes on. And for the last 2 lectures, then I'll try to see if I can find something really exciting for the last 2 lectures. How are you enjoying the laboratory? Good? Okay, good. Yeah, I mean, that was, I mean, I've been wanting to do this. I just think having a little bit of hands-on. I mean, even though this is a traditional classroom course where you do homework problems, but getting in the lab, touching things, that can be very, very good. Okay, so clearly this gets thrown away. Do you recycle these or not? I will. So I always throw things into the recycling bin because I would prefer them to be recycled, including my my sandwich. Well, it's biodegradable. I mean, the fact that not everything is recyclable, that's their fault, not mine. Okay, I digress. Let's see if. Okay. So this one at least will work until the break, and then I can go and find us another marker. Okay, so light scattering. Now, I'm going to distinguish between 2 types of light scattering. Let's get the definition down right now. There's spontaneous light scattering. And in the usual designation of this semester, that's linear. And there's something called stimulated light scattering. And this is non-linear. Well, let's start off with spontaneous. You've probably heard the story many times. So you could imagine the following thought experiment. Take a laser beam at frequency omega 0 and here's some material system. It could be the atmospheric gas, and on some days the scattering is blue, but in Ottawa the scattering is usually gray. I would say my life didn't change a bit. Rochester is noted for gray skies in the US. Okay, so here's some material. It could be a liquid, a solid, a gas, and you could look in any direction, but typically you look off to the side and you say, what is the spectrum of the light? So you send it to something called a spectrometer. And I'm in the wrong place, right? We're supposed to only use this half of the board? Okay. See, that's what happens when we have class in the other room. My memory span, it's like a Markov process. It is well, almost 0, but I've forgotten. I'll make sure I move down to this end of the board. In fact, let me do it right now. Okay, so here would be a typical spectrum. So if you plot the intensity of the scattered light as a function of frequency, you typically might find, I'll draw the picture first, and then draw these peaks on it, and then I'll show a broken scale here, and then you might find a peak out here, and at an equivalent distance here, a very small peak. And now this is centered at the laser frequency. So now just as notation, scattering to lower frequency, that is what one would normally expect, and this is known as Stokes scattering. Scattering to higher frequency is what we call anti-Stokes scattering. Now, each of these spectral features has a different name. This is called Rayleigh scattering. This is called Brillouin. This is also called Brillouin. 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 Quebecois would say Brillouin. Brillouin. Okay. And then this would be Raman. And when it's present at all, this would be the Raman Stokes, and this would be the Raman anti-Stokes. Now, each of these, and this broad feature here, with complete lack of imagination, is called the wing of the Rayleigh line. But that's too many words, so people usually abbreviate to just Rayleigh wing scattering, meaning scattering in the wing of the Rayleigh line. Now, each of these has a different physical origin. And let me just do a little chart here. Name. So Rayleigh scattering. Let's talk about the material excitation that leads to it, and what should we say? The shift from the center of frequency. So Rayleigh scattering is scattering off of density fluctuations. And there's no shift at all. It's centered at the laser frequency. Oh, of the material, of the air. So I will refine all of these, but right now that was supposed to be a bit provocative. You were supposed to say, what are you talking about? But we'll get back to that. Brillouin is scattering from sound waves. And the shift might be 1 to 10 gigahertz. Now, Brillouin scattering, we can draw a picture fairly nicely. Let's say that you have a sound wave that is propagating toward you, and now you send in the laser light here. So the laser light, a sound wave is a pressure wave, and there will be a density variation associated with a pressure wave. So it's a grating. So just think of each plane wave component of a sound wave as being a grating that is moving toward you. So the light will scatter off of this into the anti-Stokes direction. See, if the sound wave is coming toward the light, the light gets boosted upward in frequency in terms of scattering. So this would be anti-Stokes, and if the sound wave were going in this direction, the scattered light would be shifted downward in frequency and become Stokes light. So now Raman is the scattering of light from molecular vibrations. And a typical value might be 1,000 inverse centimeters. This is the typical units that people would use. And as we all know, an inverse centimeter is 30 gigahertz. Do we know that? It's 30 gigahertz. So this would be 30 terahertz would be a typical shift. Now, why is it that the Raman Stokes is strong, but the Raman anti-Stokes is weak? Well, we could symbolically show this. Here is the ground vibrational state called V equals 0. V is often a vibrational quantum number. Here is V equals 1. So this is Raman Stokes. So you scatter from the ground state to an excited state. Now, what about Raman anti-Stokes? Well, here you would start from the upper level and go back to the lower level. That's why you get a shift up in frequency. But typically, you have much more population in the ground level than you have in the excited level. And that's why the Raman Stokes is much stronger than the Raman anti-Stokes. And the relative population between the ground and the excited state is just given by the Boltzmann factor. So if this is N0, then the density in the first excited state would be N0 e to the minus, I ran out of space. So N1 is N0 e to the minus h bar omega v over kt. So h bar omega v is the energy separation between the ground and the excited state. And if you just put in the numbers that I used, 1,000 wave numbers, you'll see that this population is non-vanishing, but is considerably smaller than the ground state population. So we've done Raman, Brioan. Okay, what about Rayleigh wing? It's the orientation of anisotropic molecules. So let's imagine that you have something like carbon monoxide, CO. It's a linear molecule, but if you have a collection of molecules in a gas, they bump into one another, and so they are not all fixed in orientation. They'll be randomly in orientation, but it's more than that. They bump into each other, so they jitter one another, and the orientation is not fixed. So when light scatters off of this jittering motion of a molecule, this is what gives rise to Rayleigh wing scattering. And you see, it's just a little bit bigger than Brioan, but let's say this is also 1 to 10 gigahertz. Now, there's actually like 3 chapters in the book that deal with light scattering and both the spontaneous and the stimulated versions. And I've given you a homework problem so you can study this. But we're just going to have one lecture on all of this, just to give you the flavor of stimulated light scattering. Now, density fluctuations. Let's get back to this because it's a crucial point. Well, all of these are due to fluctuations. I mean, a sound wave is a fluctuation, but the Rayleigh scattering, it's density fluctuations. Let's take a look at why this is important. I guess the key point is that there is no scattering from a perfectly homogeneous material. And maybe you knew this already, and if you didn't know this already, you're going to learn something. And you're going to learn something that is a little bit counterintuitive. So let's imagine that you have a gas of scattering material. And I'll just isolate my attention on a thin slab of this material. And later on, you have lots of thin slabs of it. And now you have a plane wave of light coming in. And of course, in this region here, I can break it up into small regions of volume delta V. So the plane wave comes in. There are molecules here. Each molecule develops an oscillating dipole moment. An oscillating dipole moment will radiate in a dipole pattern. So some of the light would be scattered into, well, every direction, and in particular into this direction here. So boy, it sure looks as if this will scatter light. But then you realize that for any volume, actually I'll call it dV1, for any volume dV1, there's going to be some other volume, which I'll call delta V2, which will also scatter into exactly the same direction. And I will choose the location of delta V2 so that the path length difference between the two is exactly lambda over 2. And that means that you will get destructive interference between the two of these. And so for wherever I choose delta V1, I can always choose a delta V2 where you get destructive interference, except in the forward direction. So what about the forward direction? So scattering into the forward direction, well, in the forward direction, it's going to be coherent because the molecules are vibrating in phase with the incident field. And in the forward direction, phase match, if you want to call that, will be automatically satisfied they'll be oscillating in such a way that in the forward direction, the scattered light adds up coherently. So this is called coherent forward scattering. And this produces the index of refraction. So this is another way of understanding the origin of the refractive index. All semester long, including problem 1 on the midterm exam, we said, well, you can calculate the refractive index by knowing the Lorentz model and determining the susceptibility and determining the dielectric constant, taking the square root to get the refractive index. But perhaps a more proper way of understanding what's going on is that the incident light comes in, it generates a wave propagating in the forward direction. The two of these interfere with one another. There will be a phase shift between the incident light and the scattered light in the forward direction. And so when they interfere, the total light will be shifted just a little bit spatially, and that is a way of understanding the origin of the refractive index. And this idea is there's a nice treatment of this coherent forward scattering in the book of Born and Wolf. Okay, so that's the forward direction. Now let's consider this off the side. I said it's destructive, but is it complete destructive? Well, it'll be complete destructive interference only if you have exactly the same number of molecules here as you have here. So if you don't have exactly the same number of molecules, then you will get partial interference, but not complete interference. So it's actually the fluctuation in the number of molecules. So if the actual number on the average is N1, if this is the average number in this volume, the variance, the RMS fluctuation is equal to the square root of N1 bar. So if you, so this is a fun calculation which is going through in the book. You say, hey, they interfere constructively, so you'd expect it to go like N squared. You'd expect it to go like N squared, but it's actually not the total N, it's only this. So once you take the square root of N and square it, you get back to N. If you do, it doesn't pay to be too smart. If you do it the naive way, you get the right answer. Then once you realize that, that this is what's really going on, it's a much more complicated argument that gives you the same answer, but only for an ideal gas. In an ideal gas, the fluctuation in the number is equal to the square root. In a solid material, in water, there's the concept of compressibility. So the fluctuation in the number of molecules in any one small volume is going to be much smaller than the square root of delta n. So the scattering from gas per unit molecule is much, much stronger than the scattering from condensed matter per unit volume. Okay, so I think this illustrates the origin of light scattering. It tells us why fluctuations lie at the origin of light scattering. Now, let's get back to this thought of the distinction between spontaneous and stimulated light scattering. We can now refine this thought. So, spontaneous light scattering. What we mean is that the fluctuations are of thermal origin. So it's the, most obviously for the Brillouin scattering, that these sound waves are generated by the thermal excitation of the medium. Well, in concept, quantum mechanical zero-point fluctuations can also be the origin of the fluctuations that give rise to light scattering. But when you go through the numbers, you find that in most cases, it's the thermal. But in concept, at the absolute zero of temperature, the only fluctuations that are present would be the quantum zero-point fluctuations. So this is spontaneous light scattering. And now when we say stimulated light scattering, we mean that the fluctuations are induced by the laser light. So you can see now why this is nonlinear. The laser light creates the fluctuations, but then the light scatters off of those fluctuations to produce the output scattered beam. Now, a general thought is that each spontaneous scattering process has a stimulated analog. That means we could easily spend the rest of the semester talking about stimulated light scattering, because Raman, Brillouin, Rayleigh, Wing, all of them have a stimulated analog. We could go through the theory of that. And when I was younger, and had more energy, in the book I actually do a detailed analysis of each one of these. But I'm not sure that one needs a detailed analysis of each of them. I will do one of them here, and then you sort of catch on. You sort of catch on as to what's going on, and it's only the details that are different for different scattering processes. In different years, I've done it differently. I think maybe last year I did Brillouin as the example, and this year let's do Raman, just as the specific example of what we'll treat in detail. So in the old days, the good old days, 3 years ago, we used chalk. Feynman, among the Feynman rules, one of his rules that every piece of chalk is less than 1 centimeter long, because the instructor walks in the classroom, always picks up the biggest piece of chalk. The custodial staff will not put in new chalk until the old chalk is used up. So every piece of chalk becomes asymptotically smaller and smaller and smaller. It's almost like Zeno's effect, right? But it never actually goes away, does it? Okay, so stimulated Raman scattering, which I will abbreviate as SRS. So just to remind ourselves, I love these little pictorial representations. So you bring in a laser beam. interacts with a collection of molecular oscillators, and it produces output light at a frequency omega laser minus omega v, and I'll call that the Raman-Stokes frequency. Now, what is the output intensity? It's like ruining the movie for you. I'm going to tell you how the movie ends before you see the movie. I'm going to tell you the answer in case you fall asleep before the lecture is over. At least then you'll know what the answer is. So to produce the output intensity, we apply a laser beam of intensity I sub L, and we apply a very weak beam at the Stokes frequency IS of 0. We can call this the Stokes seed. It's the beam that seeds the process, and it could well be the vacuum. You pass through a length L of material, and you measure the Stokes light intensity at the output, and ignoring saturation, the Stokes intensity at the output is the Stokes intensity at the input times e to the g I laser times L. G is some coefficient. We'll call it the Raman gain factor. And a typical value might be G equals 1 centimeter per gigawatt. Okay, so if you have a few gigawatt of laser power, that's when you're going to be able to get a fair amount of Stokes light generated. Let me give you an example from my own research, going back a few years. But the L is for Ludwig. And he's very proud that he spells Fisher in the German way, not... I usually don't remember the middle names of all my students, but when someone tells you my middle name is Ludwig, somehow that sticks. Okay, so George Fisher needed, well, he needed a PhD, and he needed light at 1.9 microns to do his experiment. So we didn't have a 1.9 micron laser, but we had a neodymium YAG laser. So the way he did this was to take light at 1.06 microns, and he used a gas of hydrogen molecules at 30 atmospheres. We called this his Hindenburg machine. No one else wanted to be near the lab when he was playing with his high pressure. We've mentioned self-focusing in the window of a cell can drill a hole through the window of the cell. It creates a spark. So, George, please don't self-focus onto the window of your cell, at least if the rest of us are close by. Okay. And okay, if you go through the calculus, hydrogen has the largest Stokes shift of any known molecular species because hydrogen is very light. And you know, chemical bonds, for the most part, will have similar similar spin constants. But if you have a very light mass, you're going to boost up the frequency. So you go through the numbers, and this turns out to be 1.9 microns. And the specifics of the experiment were that he had a 40 centimeter lens, and he brings this to a loose focus in his hydrogen cell. This was 50 centimeters long. I've already told you 30 atmospheres. He collimates the light coming out. He puts it through a filter. This rejects 1.06 microns. And in the end, he ends up with lambda equals 1.9 microns, 150 microjoules of energy, 5% conversion. I guess here the input is a 30 picosecond pulse and 3 millijoules of energy. The specifics are not the issue here. It's just that this is a standard way of shifting the wavelength of a laser. If you want light at a different wavelength, you can just use Raman shifting to do it. Clearly, this is a very straightforward setup. You take the laser beam, you focus it into something, and as if by a miracle, light at the wavelength you want comes out. Okay, in the book, I list a number of materials, and I give the Raman shifts that you can achieve from these materials. Okay, so this little g is the one thing that describes the Raman process. Let's see if we can develop a theoretical method to calculate little g. By the way, the upper echelon of the university is trying to decide what to do with these lectures. It's like a white elephant. They have these lectures. Should we put them on the web? Oh, but that might violate something. I said, well, you have my permission to do it. Well, it still doesn't seem like a good idea. You say, well, okay, what do you want to do? Just put them in a safe and just hold them there? That seems like a questionable use of all this money. I mean, one student in Manitoba, that's the only reason we're doing this? I say, well, you know, we have to get our lawyers involved. You paid money to hear my lecture. Or somebody paid the money for you. Nobody pays their own money these days. That's not quite true, but in concept, you paid money to hear these lectures. So if we give it away for free, that's not fair, is it? Stanford that doesn't bother them. Harvard, it doesn't bother them. A lot of universities just put the lectures on the web, but we're in Ottawa. There are too many lawyers in Ottawa. Oh, so what's the decision? I will store them on my computer for safekeeping because they know they'll lose them. At least I won't lose the lectures, probably. Or download them quickly. I mean, they may disappear at some point, but through the end of the semester, they'll be there. So if you want them, I've warned you that they may evaporate. Well, that's what Hillary thought too. That her email messages would just disappear, but she found out otherwise. Okay, so let's develop a simple theory of stimulated Raman scattering. And I have to admit, my derivation seems unduly convoluted, but I can't find it. But I've been doing this a long time. You should have seen what it was like 10 years ago. Let's just put it that way. Okay, so basic concept. We have a laser beam E of Z and T falling onto a molecule. Let's take the atomic distance. Let's call it x of t, and let's write it as x naught, the equilibrium value, plus q of t. So the only reason I've introduced q of t is so that this oscillates around 0, whereas this oscillates around something other than 0. So let's assume that the equation of motion for the, for q of t, for the molecular coordinate, the vibrational coordinate, is d2q dt squared plus gamma dq dt plus omega v squared q is equal to f of t over m. Well, what is m? It's the reduced mass, right? But what in the world is f of t? F of t is the force that you apply to this vibrational degree of freedom. When we did the Lorentz model, you had an electron. It was clear what the force is on a free electron. But how do you calculate the force that drives this molecular vibration? And that is the subtlety of this calculation here. How to deduce so let's make an assumption. Let's assume that the polarizability alpha of t is equal to alpha 0 plus partial alpha with respect to t 0 times q of t. Now, this is the usual polarizability, as in p of t is equal to epsilon 0 alpha of t E of t. So this is a physical assumption. Think of a diatomic molecule. As the atoms move further and closer together, you'll distort the electron cloud of each atom, and you'd naturally expect that the polarizability is going to be different when they're here than when they're here. And you might even expect it to be larger when they're here than when you're here, because usually bigger things have a bigger polarizability for the scaling laws we talked about earlier in the semester. But that's just a guess, that it would be bigger. But we assume that the polarizability changes with this interatomic separation. Now, the really confusing part, and I will do my best to confuse you, the really confusing part is that this is the electronic polarizability. So this is a coupling between two different degrees of freedom, that the molecular degree of freedom modifies the electronic polarizability. I think it was 10 years after I'd written the book that I caught on to the subtlety of this statement here. So think that one through. Now, now, before we really forge ahead with a horrendous calculation, if you want to look ahead in the book, you can see how horrendous this lecture is going to turn out. Before we forge ahead with a horrendous calculation, let's see if we can develop a little bit of intuition as to what's going on here. So we know that n of t is the square root of epsilon of t. So this will be the square root of 1 plus n epsilon 0 n alpha of t. The epsilon 0 does not appear here. Well, by my convention. I choose not to embed the epsilon 0 into the alpha so that alpha has the dimensions of a volume, which justifies the intuition that bigger things have bigger polarizabilities. So then you send laser light at frequency omega into a medium made up of a number of molecules all vibrating at frequency omega v. That is going to modulate the refractive index at frequency omega v. And because of that, we'd expect that at the output, you will induce two new sidebands. In addition to omega laser, you'll have omega laser plus omega v and omega laser minus omega v. Okay, so that's the intuition, but we still have to now figure out how to deduce the force on this degree of freedom. So why is there a force? Well, let me draw a different picture. If we have light at frequency omega laser and light at frequency omega laser minus omega v, the beat note will be at the vibrational frequency. And then this beat note between omega laser and the Stokes frequency is going to tend to drive these molecules into oscillation. These two processes mutually reinforce one another. This process causes the molecules to vibrate more vigorously. Then this process creates more Stokes light. Then this process makes them vibrate all this more strongly. And then this process creates still more Stokes light. That is the story of all stimulated light scattering. In each case, you can find that there is mutual reinforcement between two processes. And not surprisingly, this leads to exponential growth of the fields that we develop. Okay, so now we have to work it out mathematically. So let's assume that our applied field is given by E of z and t is some laser amplitude e to the I k laser z minus omega laser t plus a Stokes e to the I k Stokes z minus omega Stokes t plus complex conjugate. Now, just for fun, let me calculate e squared of t. Actually, for fun, let's not do it. It has, what, 4 terms. Let's not bother to write everything down. It gets messy, and you know very well how to do it. E squared of t has a contribution that is given by a laser, a Stokes star, e to the I k z minus omega v t plus complex conjugate, and here I just defined k to be k laser minus k Stokes. So let's see why this contribution ends up producing a force on the vibrational degree of freedom. And to do this, we remind ourselves that the energy stored in the vibration is, I'll call it W, and it's the integral from 0 to E of the dipole moment in the presence of a field E prime d E prime. So PdE is the contribution to the stored energy. You integrate this from 0 field up to the final field. So this becomes, now with the epsilon 0 integral 0 to E of alpha E prime d E prime, which is 1/2 epsilon 0 alpha E squared. So maybe not so surprising. The energy stored in the vibration of a molecule is given by this expression here. So then the force on the vibrational degree of freedom which we've been calling F of t. In general, it's the partial derivative of W with respect to X. Principle of virtual work, it's sometimes called. So now if you just differentiate this, you find this is 1/2 epsilon 0, 1/2 epsilon 0, no, 1/2 epsilon 0, E squared partial alpha with respect to X at 0. And here, here I've replaced E by the time varying field because this is what we were calculating here. So let me just pause for a second while you absorb this. So here is the force on the vibrational degree of freedom, and it depends on this quantity that we introduced. So this assumption here plays a key role in telling us how to calculate the force on the vibrational degree of freedom. Okay. So once again, we care about the contribution to E squared that is near the vibrational frequency, because that will resonantly excite the vibrations of the molecule.
I'm not quite sure about the directions here. Your electric field's in the Z direction, right?
It's a scalar theory, but that's not an acceptable answer, I don't think.
I'm not sure why. I mean, I know that the force, like you can, the force.
Oh, x is not a Cartesian coordinate. X was the distance. X was the distance between the two molecules. Yeah. Okay, so that's why my seeming irrelevant answer actually was the answer. Where did I? So the force at a vibrational frequency we'll just take the part that we care about. So F of t is 1/2 epsilon 0 partial alpha with respect to x 0, a laser, a Stokes star, e to the I kz minus omega v t plus complex conjugate. Now, of course, I've long ago erased the equation of motion. Let me write it down again. So the equation of motion is d2q dt squared plus gamma dq dt plus omega v squared q is equal to f of t over m. And we now know what to use for f of t. So we now just solve this for the sinusoidal steady state. So we set q of t equals q of omega e to the I kz minus omega t. Actually, let's change this now. Let's just put omega here, and omega now will be defined to be omega laser minus omega Stokes. In other words, I'm not assuming that we're exactly at the vibrational frequency. Omega laser is the laser frequency, omega s is the Stokes frequency. This is just the difference between the two of them. So it's just omega that appears here. Okay, so substitute this into this equation, and I won't show the steps because they're so obvious, but Q of omega is then 1/2 epsilon 0 over m, partial alpha with respect to x 0, a laser, a Stokes star, omega v squared minus omega squared minus I omega gamma. Okay. You know the procedure now. We want to write this in terms of a susceptibility. So let's let P this is a little bit subtle, is epsilon 0 times n times alpha of t times e of t, which we can write as epsilon 0 n alpha 0 plus partial alpha with respect to x 0 q of t times e of t. Now, of course, e of t has two different frequency components. Q of t has two different frequency components. So there's going to be 4 different terms that show up here. And we will take a look at all of them before the lecture comes to an end. Let's consider first one contribution to P of t. I said there's 4 of them. This contribution we'll write as, well, let's just call it P Stokes of t is P at omega s e to the minus I omega st plus complex conjugate. And then P at omega Stokes for the term I want to look at is epsilon 0 n partial alpha with respect to x 0, a laser, q star of omega. And we'll just note that this would go like omega laser, and q star is going to go like minus, well, approximately omega v. So this really is of the Stokes frequency. That's why you need to put the complex conjugate here. So just cross that out, but just to remind yourself that that is where this comes from. And then, let's see, put all of this together. You put all of this together, and you get I don't believe it, but this is what you get, n over 2m, epsilon 0 squared. maybe I do believe it. Partial alpha with respect to x, 0. Last time I taught this, I put a note to myself that I should go back and take a look at this. E to the I k Stokes z over omega v squared minus omega squared plus I omega gamma. Okay, so this looks like your typical typical resonance factor for a harmonic oscillator. We can simplify this form. Close to resonance, the difference of two squares. So the trick you've done many, many times in your life. We can write this as P of omega s is n epsilon 0 squared over 12m partial alpha with respect to x 0 squared divided by I'm sorry 24 m omega v omega Stokes minus omega laser minus omega v plus I gamma over 2. So you can now break this into its real and imaginary parts, and you find a plot that looks something like this. So the imaginary part is now negative going, and then the real part looks something like this. So this is the imaginary part. Sorry. I wanted to write this in terms of the Raman susceptibility. I wrote down the right-hand side of this. I copied down the left-hand side wrong. So this is the Raman susceptibility. I guess I'm supposed to define that. P of omega s equals 6 epsilon 0 pi Raman at omega s a laser squared a Stokes e to the I k Stokes z. Sorry, I left out a line. We had derived an expression for the polarization at the Stokes frequency. I now choose to write the polarization as a nonlinear susceptibility. Nonlinear susceptibility is defined in this manner. I'll call this chi Raman at omega s, meaning that this is defined to be chi 3 at omega s equals omega s plus omega laser minus omega laser. So this would be the standard form for a cross-action effect susceptibility. I'll just call it chi Raman at the Stokes frequency so that we don't have to write it out all the time. Defining it in this way, the Raman susceptibility takes on this form. So this is the imaginary part of chi Raman, and this is the real part of chi Raman at omega s. Okay, so since we are almost through a course in nonlinear optics, once you know the nonlinear susceptibility, you know how to calculate anything. So knowing this, it's just 2 steps away from deriving a coupled amplitude equation. So let's do that. And I won't go through all the steps. We've done it too many times. Knowing this, you know what the nonlinear polarization is. You can use that in the wave equation. And after a few steps, you find that dAs dz can be written as minus alpha s times as my apologies, this is a different alpha. I'm using the same letter of the alphabet for polarizability as I am for an absorption coefficient. Well, this one has an S on it. I guess if you need a justification, that is the justification, where alpha S then is minus 3I omega S over C chi Raman at omega S A laser squared. Okay, so I've written the equation this way. This looks like the equation for a wave that gets attenuated with an absorption coefficient given by alpha sub s. But you come over here and you note that the imaginary part of chi is negative. That means that changes the sign of alpha sub s, and that means that is actually amplified. So this justifies the statement that I made at the beginning of the lecture, that if you plot the Stokes intensity as a function of z, it's going to see amplification at a rate. Well, this was the amplitude, this is intensity. So I guess this goes like e to the 2 alpha Stokes z, something like this. Okay, so we're a quarter of the way done with a fraction of the lecture. We said that there are 4 terms when you look at all these together. We've seen that the most obvious one is the one that will lead to amplification of the Stokes wave is given by this form here, which we can write in terms of all of the parameters of the problem at hand. The key coupling strength, again, is this one here. The dependence of the polarizability on the displacement of the 2 particles. This one? This 2? It's because if I were a rational person, I would have put the 2 here, but I didn't. I have to look at the book. I usually define this to be the intensity absorption coefficient. The way I wrote this equation, it's an amplitude absorption coefficient. So then you need the factor of 2 here. Yeah, because intensity is the square of the intensity is the square. Okay, so where can I write this? Okay, so we've seen that the Stokes wave gets amplified as it propagates through the material. Now, let's repeat the calculation and see what happens for the anti-Stokes frequency. This was the polarization at the Stokes. Let's see what the polarization is like at the anti-Stokes. Well, the calculation we performed still works because we never made use of the fact that the field I called the Stokes field was at a lower frequency than the laser field. So I can just pretend that it's the other way around and just change the name. And the easiest way to do this is to set omega laser minus omega Stokes equal to the negative of omega laser minus omega anti-Stokes. So this is the opposite sideband. And you look at the equation I just erased, and this tells you that chi Raman at omega A is chi Raman at omega S complex conjugate. So the real part stays the same, but the imaginary part changes sign. And this means that dAA dz I can write as minus alpha A sub A, where alpha sub A, this is now the anti-Stokes absorption coefficient. And this anti-Stokes absorption coefficient is given by, well, just write as the negative of alpha, the S seems to have disappeared, the negative of alpha S. So the anti-Stokes wave experiences attenuation. So maybe this is not so surprising that this wave here gets amplified. I'm letting this be omega laser and this be omega Stokes. But if you do the experiment the other way around, and the population starts here, so here is omega laser, and here is omega Did I draw the picture right? Yes. Here you start here and you end up here, and omega anti-Stokes is actually attenuated. How can you see that? Well, I think it's actually easier if you draw the picture the other way around. Here is omega A. Here's omega laser. Right? These are equivalent pictures. These are equivalent pictures, just the time reversed. So here you see that the wave that points down is the one that is amplified. That means that this process here will suck energy out of the anti-Stokes wave and put the energy into the laser wave. So this is a pictorial version of what I meant in words here. That the calculation didn't presuppose which one was which. The calculation says that that the lower frequency wave becomes amplified. And here, the lower frequency wave is the laser. So here the laser gets amplified at the expense of the anti-Stokes. Here the Stokes wave gets amplified at the expense of the laser. Okay, so what? So it's 4 o'clock. It's time for us to take our break. Okay, so I'm going to go get better markers for the second.